solve it yesterday? How do I? Ooh, what do I? Oh, we already did that.
0, -1.
Okay, how do I do 0, -1?
Add 0 and -1.
Because that's a differential equation. Take the 0, take the -1, add them. So then the slope is -1. How do I do -1? Down. That's up. Okay, so down 1, right 1. I need to have what kind of slope? Downhill slope, as opposed to uphill slope. Negative? Positive? Got it. So, down 1, right 1, and I connect it, right? No, that's not a baby tangent. I pretend connect, right? And then beep. Question, what else is going to have a slope or did have a slope of -1? The diagonal, right? Why is it the diagonal? Well, this one just has that pattern because y equals -x, whatever, or along this diagonal line as it shifted, they're all going to share. Not every differential equation, but this one. The AP likes to call this for what values of y, for what values of x, something like that, where you make a little baby equation and say, hey, look, it'll always be true. What was the slope at -2, 0? So how do I do that slope? Down to right 1. And then we have that, be that diagonal line, right? And then I have -3. To some extent, you kind of have to just start approximating. Going more negative, and being like, that's the best I can do. Wait a minute, I missed one. -3. Down 3, over 1. So how's it look? Nice. Now wait, we're not done. Why am I picking up the blue pen? There's a clue. And the clue says, hey, this guy goes through. Now, hold on, pause. Is this a connect the dot type problem? No. I'm supposed to, what did we write down yesterday? Go with the flow, exactly. Did you guys ever look at yesterday? We didn't talk about it explicitly. The vector field? The slope field? Ooh, the wind map? Ooh, on the front page. It's around the Middle East, I have no idea why, but anyway. The wind map in the Middle East. Probably a while ago. Ooh, October 25th, 2006, 3 p.m. Anyway, Wonderground. Hey, I used that app. I'm like, well, Underground. It has like a lot of different. Anyway, yeah. The wind map. Does the wind go like arrow to arrow to arrow to arrow?
That'd be really awkward.
No, that's so awkward. The wind flows, right? So what are we supposed to do for a slope field? Flow. But you guys just learn other names for slope field. Trajectory space, slope field, vector field, flow field, direction field. Ooh, lots of different names for these little baby tangents. Anyway, seems like there are lots of different uses for them too. If I was to follow the flow, do you guys see why I'm doing a curve like this, skimming this line? Do you see why I'm doing that? Why would I skim this line?
This is a tangent line.
Because it's a tangent line. It's supposed to skim, right? I'm going in between some. I'm touching others. Wait, why? Why did I level off right here? I didn't go up here to level off. I leveled off right here. Why? All of these are going to be leveling off locations. And so this guy would go down, level off, right in that diagonal line, level off. And then what am I doing? I don't know. I'm just kind of going with the flow. Wait, you left off this whole area of the map. It doesn't make sense. Pause. Look at your wind map. Okay, that's not really good. Look at your vector field for the wind. I want you to put your finger on, I don't even know, Saudi Arabia. Boop. Follow the wind. Where does it go? Wait, why did you just miss Iran? Why did you miss Syria? Why did you miss Iraq? Because I was following the wind. You just follow the flow wherever it goes, wherever it leads you. What if the initial point was something like -2, -1?
You follow the flow?
Yeah, where would the flow go? Down, right? Do you see it? The flow would go down. Guys, this is a much more complicated differential equation than you have ever seen because the ones that we have seen up to this point are much more like, what was example number 1's pretty one? Not the one we did, but the big one. The ones we've seen, the ones that we've done, the ones that we've solved with integrals have been super basic like this one. how is this different than like that crazy Middle East wind pattern or like the one that we see now? If you pick a point, what's it going to look like? Anywhere you pick a point on this slope field. What are all of these going to look like? The same. They're all going to be cubics. They're all going to be like, oh, I'm going up and I'm going over and I'm going up. They're all cubics. Why? Because what's the antiderivative of x squared? Remember the guy that we saw yesterday? 1/3 x cubed plus c. So what's the only thing that can change in that equation? The plus c. But as you add 1, add 2, add 3, isn't it all going to be 1/3 x cubed just up or down? Right? Is this that easy? Is it all the same? Just go up and go down? No. The wind map. The wind in the Middle East. Is it as easy as up and down the exact same shape? No. There are much harder differential equations where it's not as easy as just a plus c. Now, the c always comes from having solved an indefinite integral. It starts as a plus c, but there could be nasty stuff on this side with y's and nasty stuff on this side with x's, and when we try to get the y by itself to get a function, the c gets stuck. The c is maybe like a piecewise function. The c maybe is sometimes being divided or in a power or multiplied. The c ends up all sorts of places where I start square rooting both sides or taking ln of both sides or doing e to the power of both sides. Or some differential equations, y can't even be gotten by itself. The implicit derivatives. Here's a long story short. This guy right here, if I were you, and you have one of those special highlighter color pens, etc., about AP tips and tricks, this differential equation they love to give to you sometimes, and it's actually one that you cannot solve by hand. Meaning, you cannot find the solution. You cannot find the solution with where you are in calculus. You cannot put a dy dx, move the dx to the other side, and somehow take an integral. You can't. Because the x plus y is tied together, and I cannot separate it in a legal way to integrate. We'll talk more about that in section 5.2. But this is one type. Whenever there's an x plus or minus a y, any x term, 5x, 6x squared, whatever, plus or minus any y term, it is impossible to solve. We can only check, what did we say yesterday? We can only check, use, or analyze. We cannot find. But the AP is going to make it sound like, or you're going to think you can find, and you're going to get stuck, and it's going to be dangerous. But why am I saying that? If you cannot solve for the solution of this by hand with the skills that you have, what can you do? You can see it. I can see the solution, can't you? I can see it. We just did it. I didn't need to integrate. I didn't need to anti-derive to see how it behaves. All I needed were the rates in the slope field, and I'd be like, hey, that's how it's going to behave. Ish. I mean, not perfect, but yeah, pretty much that's it. That's how it's going to move. That's how it's going to behave. If I were to go here, it's going to do something else crazy. If I go over here, maybe it's going to have something else kind of weird going on, or maybe it's going to look a lot like that. But even if I can't solve it by hand, I can still make a slope field that follows the flow, and that's kind of one of the applications. Because some integrals are impossible to anti-derive at all, and some just require further, deeper calculus than we're going to cover this year. You guys were supposed to keep graphing these guys last night, true? And when you were graphing these last night, let's see how you did. If you plug in 0, 0 to this guy, 0 plus 0 minus 1 is going to be a negative 1. Bloop, 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 bloop. If you plugged in 1, you should have gotten 1 plus 1 is 2 minus 1 is positive 1. Up 1 over 1. Same thing with, just kidding. 0, 1 is going to end up being a 0. 0, negative 1 is going to end up being a 0. Negative 1. Oh, I totally did that wrong. Yeah, 1, 0. Thank you. 1, 0 is just 0, yeah? There we go. And then 1, 1 is going to be that positive 1. Negative 1, 1 is going to be that positive 1, positive 1, positive 1. How does that look? Confusing anybody? How do we follow the flow on this one? Wait a minute, what does it say after we sketch the slope field? It says to sketch the solution curve, we're supposed to follow the flow, right? Solutions to differential equations flow through these guys. So through the origin, don't I have to somehow skim this, guys? Right? I have to skim it. But wait a minute. Aren't I supposed to like do some leveling off somehow in this ish region?
Oh.
So maybe it's gonna be like a, and then I see positive slopes, so maybe it's gonna be like, and then this is gonna somehow level off, so maybe it's gonna be like a, and then it's gonna go down, so maybe it's gonna be like a, I don't know. I mean, I really wish I had a better slope field, but I really liked making this one because I only had 9 points. It was like boom, 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 done, but it wasn't enough to give me a clear picture. I was like, okay, I'm leveling off, okay, and then I'm going up, okay, and then I'm leveling off, all right, and then I'm going down. It's a lot more helpful to have a lot more slope fields, but that's why we have things called computers and technology. And look at that wind map. That was not done by hand by somebody, right? The one in the Middle East. That was definitely done by technology. So the more slopes you have, the better the picture, but if they're trying to test us and whether or not we can do this by hand, they're not going to give us tons and tons, so it's not going to give us an ideal picture. The AP hasn't given you one this abstract as far as trying to sketch and follow the flow. I was just seeing if you guys kind of saw the dilemma of not having very many points and not always having a clear picture, right? So how does everything change in example number 4? Are you making them anymore? You're matching them. Hey, we matched F yesterday. Can you guys take a second and think about, wait a minute. We have to think of 2 different things. Kind of like integration as net change. We thought about, hey, are we being given rates or are we being given amounts? And we had to think of it in context. If we're given amounts, we have to take slopes to do rates. If we're given rates, we have to do integrals to think of amounts. For differential equation questions, we have to kind of think the same thing. Are we trying to match the differential equations? Wait, who are differential equations again? Those guys that contain... maybe y prime, maybe y double prime, but at our level, y prime. At our level, dy dx. So differential equations that involve derivatives. Are they having us match to the differential equations or to the originals? Yeah, originals because no derivatives. But pause, what's the difference between the 2? Yesterday, did you write it down when I did? What does dy dx find and what does the original solution do? dy dx finds what you just used dy dx. The slopes of the tangent lines. The slopes of the tangent lines. So if I'm thinking or matching to dy dx, I need to actually look at the slopes. Where they're up, well, that means positive dy dx. Where they're flat, that means a 0 dy dx. Where they're down, down, that means a negative dy dx. But what does the solution do? What does the original do? It doesn't get the slopes. It think the wind. What does it do? Blows. So how was Adam able to make that sign match yesterday or the day before? Maybe both. What was flowing? That's uncurved. Ready, set. I want you guys to match the second one and match example 5. Match the second one and match example 5. If you're bored, you can also be doing slope fields and working on that worksheet on Tuesday. Almost there. Following the flow is usually pretty easy as long as you know what the y equals looks like. If you don't know what the y equals looks like, well, it could be a little dicey. Yeah, basically. Couple more seconds, but if you've gotten these two done, why don't you go ahead and pop ahead to the next one and say, am I still following the flow? What are you matching it to? If it's shifted.
Oh, good morning, my name is Sophia.
You made it match? Partially. Part of it is making a slope field, so you guys will have to kind of make some dot graphs on your own. But part of it is matching.
Is there a way to make that look on your calculator?
There are things called slope field programs, which are kind of nice, but at the same time, the AP will never ask for a slope field when you're allowed to use your calculator because they know there are programs. And they're one of those that you download. So, like, in years past, I've had people download them, but I'm like, I don't know if it really helps. Because ultimately, you're not going to be able to use it. For those of you guys that are watching the video, I'm multitasking while they're working on the problems that are frozen on the screen. So feel free to go back and just pause to work. We're going to go ahead and check their answers in about 30 seconds.
Is it gonna be Abby salad?
Yay! That's exciting. Are people allowed to know it's you?
Yeah, but I'm just not allowed to talk while.
Okay, that makes sense. Because otherwise you might pick you up.
I know.
Alright, here we go.
I'm not allowed to talk. I want to have a cow costume. In the cow costume. Because it's like, like last time you said, Abby talked to me. No.
At least you have to be like those like British soldiers where you can't smile. I could never.
Are they going to fire you?
Alright, number two. Number two. What do you guys match it with? D. Yeah, because it's a cubic, right?
Yeah.
So D goes with number 2, and F goes with number 1. But how about the next guy?
E.
Yeah, definitely not any of these guys, right? Although some of you might have thought him an E, but an E with a negative on the inside flips it horizontally, not vertically. Flips it horizontally, not vertically. Out in the back's check. Let's keep going now. Did you guys keep looking at example number 6? What changed?
You matching everything. The derivative.
You're matching to the differential equation, and what does dy dx find? I can't look at the flow, I have to look at the slopes. Now you might be like, I don't get the difference. Like I'm looking at the slopes when I follow the flow. I have to think of the slopes. Not the flow. Can I give you an example real quick?
Please.
Number 3 matches with A. How did I do that? How did I know? Number 3 matches with A. I didn't have it memorized. It took me a second. I saw something. I was like, oh, hey, this happens when this is true. Let's see which one matches. The slope is kind of. Think horizontal asymptote. What are those slopes? 0. The slopes are 0 when? When y equals, it looks 2-ish. If I plug in y equals 2, that's the only one that'll give me 0. Now, 2-ish, I mean, they're not exactly showing you tick marks. I mean, they kind of are. Okay, I think that's 1, I think that's 2, I think that's 3. But still, the only one where y equals a number will always give me 0. When I subtract, when I subtract 2, I'll always get 0. Can anybody find another match?
V, I, and D.
V, I, and D. V goes with,
V, I.
Okay. That's the easy one. Goes with what? 6 goes with D. Now, that was like a freebie. That was a freebie. Because look at all of these. Are any of these trigonometric besides D? But here's the weird thing. Wait a minute. Isn't D like an upside down cosine curve? It's starting like displaced, but it's upside down. I don't get it. This says sine.
Because if you antiderive it, you'll get negative.
If I antiderive sine, I get negative cosine. Negative cosine follows the flow. Sometimes you can think about what the original would be, and then be like, oh, I see it.
Right.
Or you can just be like the only trigonometric one. Well, I hope that's right. But what else? C is 4? Why? This is the flow.
The flow.
Look at the tangents.
And that you, this is what happens when you look at the flow.
You're looking at the flow, right? If that one's not, which one is? Adam said diagonal, and kind of diagonal, but then look here. Doesn't this one change on the diagonal?
Yeah.
Which one doesn't change on the diagonal? Pause. 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 Think carefully. Oh, wait a minute. Which one are you guys trying to match it with? 4 or 5? 4. Oh, okay. I was looking at 5.
Oh.
Well, we just made a match with B. Sorry. My bad. You're still wrong, though. This one doesn't match with 4. 4 is only dependent on x. So if I was to plug in x equals 1. 1, 1 should be a slope of 1. 1, 0 should be a slope of 1. 1, 1 should be a slope of 1. 1, 2 should be a slope of 1. 1, 3 should be a slope of 1. 1, negative 1 should be a slope of 1. Wait a minute, this one goes positive, then negative, then maybe I don't, nope, that doesn't work. 2? Yes.
We did.
Oh, you didn't mean to, you meant to. Why does this one match with 4? If x equals 1, what's true about all the slopes? If x equals 0, what's true about all the slopes? If x is negative 1, it's true about all the slopes. You see it?
Yeah.
Now, why is thinking that C goes with 2? Can you give me a reason why you thought that?
Because when you look at the middle, there's like no line.
0 over 0? He's kind of looking at the origin, and he's like, wait a minute, I don't see a slope at the origin at all. Isn't only a 0 over 0 undefined? E to the 0 is 1. 0 minus 0 is 0. Nice. But can anybody make a defense if we covered up the origin and you didn't look at the origin? Why else would number 2 have to match with C? Ready?
Oh, because like with all the ones that are where y equals x, it's like over 1. And so since it's being divided.
So Adam thought like, hey, y equals x line, y over x, x over y is just going to be 1 over 1. So he saw that. That was the diagonal he and Vika were looking at. And also, guys, what are the signs of x's and y's in the first quadrant? How about what are the signs of x and y in the second quadrant? Third quadrant? Fourth quadrant? What's a positive over a positive? All up. Hey, they're all up. What's a negative over a positive? All down. Oh, they're all down. What's a negative over a negative? Oh, they're all up again. What's a positive over a... You guys can think of all sorts of different things. Looking at the origin, I know it's 0, 0. Looking at when y is 0. Looking at when x is 0. Looking at when x is y and y is x. Looking at the quadrants at the signs. Lots of different ways to make these matches. I have some little tricks on the next page as far as summarizing some of these ideas. Has anybody figured out E? E is 5. This is what... Oh, did I put 5 instead of 6? I didn't keep writing. E is 5 because 1, 1, 2, 2, 3, 3, 4, 4. They're all going to be 0. Y equals x. Y minus x. If they're the same, it will equal 0. You can follow those diagonal lines of that y equals x nature, all the same, all the same, all the same, all the same, all the same. that y equals x line is going to be translated through and they're all going to equal the same. We actually did one like that just a little bit ago, but we didn't have this y equals x. We had y equals negative x. It was a plus instead. But yeah, these travel in diagonal lines. So these travel in terms of x, travel in, vertical lines. These guys, the addition subtraction, travel in diagonal lines. Anytime you're dependent only on y, travel in horizontal lines. This guy changes based on the quadrant. He doesn't know. That one was trigonometric. He was pretty easy. How have we not made this match yet? No, it can't look like E because E is the derivative. But question, who's also the original? E. Got it. No. Don't you see the E's move? There it is. You can follow the flow and anti-derive that one. Sometimes you can anti-derive, but most of the time, especially when you start having x's and y's, or even just y's, you're not used to that. This guy, the antiderivative would be e to the x plus c. This guy, the antiderivative was negative cosine of x. This guy, the antiderivative would be 1/2 x squared plus c. But I don't want you to anti-derive that. You can't. I don't want you to anti-derive that. You don't know how yet, most of you. And I don't want you to anti-derive that. You don't know how yet, most of you. Matching to the slopes, a little bit trickier. Now, you don't necessarily need to memorize this page. I'm just trying to give you like verbal clues about some of the steps we just did. But before that, even just giving you the different possible questions that you might be given with slope fields. You could be given a differential equation. You could be given, remember, that's somebody with a derivative, but for us in our level, it'll be like some sort of y prime, some sort of dy dx. Choosing a slope field. Hey, that's like what we just did. That was example, what was that example? 4? 6? Thank you. Like example 6. You could be given a solution, a y equals, you have to choose a slope field. That would be like example 5. If you're choosing a slope field from a differential equation, we have to look at slope patterns, like we just did. If we're given a solution function, or we're trying to match with a solution function, we're trying to follow the flow. And the same basic idea happens. If you guys notice, like you could be given the solution or given the differential finding the slope field, or you could be given the slope field finding the differential equation. I guess technically, example 6 was more like that. But either way, you're just trying to match one to the other, so it's kind of similar. So we'll still put example 6 and example 5. But basically, you're either going to differential equations, coming from differential equations, or going to solutions, or coming from solutions. You still need to think, about solutions. We're following the flow. In differential equations, we're looking at slope patterns. And then, John, in response to your question earlier, there are programs that have been created for your calculator and or cool websites like Wolfram Alpha that you can find slope fields on. Just plug in a differential equation or plug in a solution function and find the differential equation. But once again, I've never seen the AP give you a slope field question on any part where you could be using your calculator for that very purpose. They know what's out there and they say, yeah, good try. It's going to be by hand. Going to be right. Thank you, whoever taped my thing that I put yesterday. Someone ran me that I appreciate it. I'll just make all my Okay. So I'm going to dual page it, just in case you want to grab anything from the page before. But this is what I was talking about as far as verbalizing the clues. Where are the slopes? 0. Look for where they're flat and be like, what's going on? And can I match the differential equation with that information? Look at where the slopes are positive. Look at where the slopes are negative. Look at where the slopes travel along the x-axis or along the y-axis. Think about what those things mean. If the slopes are 0, if the slopes are flat, or I should say the tangent lines are flat, then I know that dy dx has to equal 0 wherever that's happening. If the slopes are along the x-axis, that means they're all going to be the same, or you're going to be thinking about when y is 0. Y-axis, thinking about when x is 0. If you're only dependent on x, if you have some sort of f prime of x and x alone, you know you're going to be traveling in those x equals vertical lines. But if it's some sort of f prime of y and y alone, you're going to be traveling in horizontal lines. You can also add in that whole diagonal line thing, but that's a little bit tricky. I can't just say all f prime of x, y's. It's only the ones where you're adding or subtracting. But where the slopes are positive, right? Where the slopes are negative, we can think the dy dx has to be positive or the dy dx has to be negative. And I tend to look at quadrants, thinking about quadrant 1, 2, 3 every now and then. Thinking about the quadrants aren't enough. And that you have to actually start picking out specific points, because in quadrant 1, it's both sloped up and sloped down. And you're like, ooh, dicey. It doesn't just have to do with a positive x, positive y. It also has to do with how big x is or how big y is. But anyway, those are all different things that you guys kind of picked out as far as how you made them match. So I'm curious, if you go on to example 7, can you make those matches a little bit faster? You guys have it in your worksheet. You don't need to go and see it up here. I know it's kind of zoomed out. P.S. Melanie Tadro is still selling chocolate. They'll be here all day. $1 a candy bar. On the left. Zoom in. If you guys finish that one, you can keep on peeking down below at the next make it match, which is a little bit more interesting. Just a little bit more. The rest. Why were you supposed to match number 1 with letter B real fast? Vertical. Only x. So plug in 1x, and for all of those points in that line, it's all going to be the same thing. Okay. Which other one was supposed to be pretty fast? C is 2, because those ones are traveling horizontally. One y value, y equals 0, y equals 1, y equals 2. They're all going to be the same thing. These ones are a little more interesting unless you wrote down that extra clue I didn't. Whenever you have plus or minus, what's that traveling in? diagonal lines. Maybe real quick you can match that with 4. Does it make sense that this is x over y? Wait a minute. Kind of like when y equals x, if I plug in y and x are the same thing, it's going to be -1, -1, -1. But maybe easier, when x is 0, the whole thing is 0. When y is 0, the whole thing is undefined. Do you guys see how this goes straight up and down? It goes straight up and down at y equals 0. So we don't just have zeros we can look out for, we also have undefineds we can look out for. And then you can also think about the signs. In the first quadrant, positive over a positive over a positive times a negative. They better all be negative. But I know, it's also the last one. The AP gets real mean when they all kind of look the same and are just a little bit different. And then you have all these different graphs to match. That's when they like to get really mean. But down here, example 8, it got a little more interesting, right? The slope field for a differential equation is shown at right. Which statement is true? 1, 2, 3, 2, 1, 2. For x less than 0, what part of the graph am I talking about? What 2 quadrants will x be less than 0? Yeah, if x is less than 0, x's are negatives. What quadrants are x's negatives? Second and third. So I'm looking at second and third quadrants. All solutions level off near the x-axis. We'll get back to that. For all y greater than 0, where is y greater than 0? Quadrants 1 and 2 above the x-axis. Okay, so look at quadrants 2 and 3. Are the solutions, wait a minute, solutions, aren't the solutions the flow? Are the solutions decreasing in 2 and 3? These ones are, but not quadrant 2. One's a no. Not for all. Not all solutions. These ones are, but these ones are not. Nope. Number 2, all solutions level off near the x-axis. No, these ones are going away, away, away. But wait a minute. Any solution, any point you choose, if you follow the flow, will it level off near the x-axis? Yes, it doesn't say where. It just says that it does. Do they all level off? Yes. Every single one is going to level off as it gets closer to the x-axis. That's true. So right away, we know it's not going to be that, it's not going to be that, it's not going to be that. 50% chance. For all y greater than 0, are all solutions increasing? Yes. Dun, 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 dun. Solutions, you follow the flow. In quadrants 1 and 2, any one you choose, they're all going up. They're all going up. How are we doing? Is it kind of making sense? Example 9 gets a little bit interesting. The AP loves to ask things kind of like this. Vertical. If you have vertical segments, aka the slope is what? Vertical lines have what? What makes an undefined slope? 0.
Number.
Okay, 0 over 0, number over 0, what's in the bottom?
0.
So what do I do? What's the relationship for all the vertical ones? Y is equal to -2x. Dun, 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 dun. That easy if you get the concept. Vertical tangent line, the slope is undefined, the slope is undefined, it's at the bottom equal to 0. The AP loves to ask this as like a part A to a FRQ. Oh, but this one gets a little more interesting. Oh, wait a minute. Okay, they're talking about -2 and +2. So maybe I should just like mark those. So there's +2. Here's -2. Here's 0, right? And I'm just doing that because I see 0s and -2s and +2s. What are they saying about this? Y is 0. Y is 0. Wait, don't I only see something like that when I'm thinking about a... So they're saying that the point at 0 is greater than 0? Can I just pick one? Sure. Something higher. Okay, I don't know. It's one of these guys. Somebody that's up here. Okay, follow the flow. Follow the flow. Why? Because check it. Aren't they asking you about about the solution, aren't they asking you about the flows? Does that make sense? Okay, so what's the flow as x goes to positive infinity? It's not 0. What are they smoking? Nope. How about number 2? Oh, wait. My initial condition is moved. Where's my initial condition this time? Between -2, so somewhere here? Okay. Now follow the flow. Which way? To the right. X is going to positive infinity. Where's it headed? It's headed to like a horizontal asymptote. You see it? So that's true. Okay, I like you. So you guys tell me about number 3.
It's below negative.
Is it? Follow the flow. Is it a yes or is it a no? Follow the flow. You can go left, but where's the limit tell me to go? To the right. No, don't assume. Look at it. If x is going to infinity, where's the flow going to go? Any of those. -2. Oh, but wait, it's going to -2 and not 0?
Versus 2. B.
What's homework? Playing with slope fields, maybe in the packet. You have a packet. You can work on it today as you go throughout your day. There's some matching in the packet, but when's the packet due?
Tuesday.
Friday.
Tuesday. So what's due Monday?
Work.
Bookwork. I'll see you guys later. It's on Google Classroom, right?
Yes.
Cool. Happy Friday.